Uh, so in this week, first we'll cover the lambda expression. Okay. So lambda expression is a way of writing a small function. Like oftentimes, for example, when you are using the methods like sort, filter, or accumulate, you will have to write a small function uh, to perform an operation on an array. Okay, so a lambda is a way of writing a small function which is also anonymous, so you don't need to give a name to the function. Wait, so here it's written C++11 introduced lambdas as a syntactically lightweight way to define functions on the fly. So a lambda expression has the form like this. First we have a capture list. First we have a capture list, then a parameter list, then the return type, and then the function body. So the capture list and the parameter list can be empty also. Um, now what is the use of all these things? So a lambda expression is like a small anonymous function. So function will have parameters, right? So this is the parameter list. So that is how we specify the parameters or the arguments of the function. The return type obviously specifies the return type of the function, like what it is going to return, and the function body is the body. Now, so the only special thing here is the capture list. The capture list is a way to pass on some context of the program. So you can pass on some variables. You can write some variables in the capture list, and they will be available in the function body also. For example, here you can see that in this line we have written a code to find the remainder of a value, and then in square brackets we have written n. So it captures the value of the n, like this n equal to 7. So it kind of captures the context of the program where it's running, captures the context of the program. And then in the parameter list we have int m. So then it takes on the argument, and then it returns the integer. So there is a right arrow int, and then the function body is return m mod n. So this is like a, as you can see, this is like a remainder function only, uh, which is which divides by 7 and gives the remainder. Here also there is another example where the function's name is accumulate, ACC for accumulate, and then uh, it it captures the value of s. It also takes an argument m, and then it returns s plus n. Now the difference here is that in the first case we don't have a ampersand in the capture list, so it means that the capture happens by value, and in the second case we have an ampersand here, which means that the capture is done by reference. So what it means is that after writing this function, if the value of s changes, then that change will be reflected in the function also. That won't happen over here. Okay, let me continue now. So the rest of the this PPT is about closure objects which basically deal with how is this capturing done, like the details of the capturing process. So I think you can go over this on your own. Okay, the closure objects. This is another thing. So you can specify some default values of the in the capture list. So if you write over here just a ampersand without any variable, so it means that whatever variables you use inside the function body, they will be captured by reference. Now in the second case, if you write a equal to within the square brackets, then whatever variables are used in the function body, they will be captured by value. Okay, so first one is default all by reference, second one is default all by value. Next we have a list of specific identifiers by value or reference. So we can write a name of a identifier like a variable, so that then only that will be captured. We can also write it in the reference format. We can also write a mixed type, like few variables we can write by value and then few variables by reference. We can also do this. We can say that by default, capture all by reference, and then one value you can capture by value.
Hello,
Hello,
hello.
hello, hello.
Sir, one doubt.
Huh, say,
Uh, Sir, yeah, day before yesterday, I have shared you some question.
hmm.
Were you able to find the answer?
No, I haven't found it yet.
Sir, can you discuss it here?
Okay, wait, wait. I will do it. Wait.
Can I share my screen? Hello, sir. Should I share my screen?
Okay, Thakur, so like I don't know what to discuss because
Sir,
I
can
haven't
I
found.
share my Sir, can I share my screen? I have a question.
Is it a different question?
Yes, but it will hardly take 10 minutes. 5 to 10 minutes.
Okay, okay.
Should I share?
Yes, wait.
Share. Should I share, sir?
Yes, wait.
Okay, 1 minute. Sir, is it visible? Hello?
Wait.
Sir, is it visible?
Yes, yes, it's visible.
Sir, in this, there is a, we have assigned PB pointer which is of base class type or drive class type as address of base class object. So why it is written error here? Sir, we know that f function is a virtual function, and in drive class also f will be a virtual function. So PB arrow pointer f2
So this is
will
the
ex
same doubt only, na? So
yes, yes. So why it is giving error, sir? I think it can access base class f function because PB, because virtual functions are dynamically
correct. This
bound.
I told you that I haven't seen it yet. So
Sir,
I
I want to ask, is my concept is correct?
Yes,
But
yes, it's correct.
which is I am saying.
Yes,
So
it's
f is a virtual function, so it will bind to a pointer function to which it is invoked by using dynamic binding.
yes, yes.
So sir, why it is written error here?
I don't know.
Sir, you said you will run.
Yes, I have not been able to run it yet. Okay, uh, I will do it
Okay,
soon.
okay, sir. When you will do, please tell me.
Mhm.
Okay, sir. So which week you are discussing right now?
11.
11. Okay, sir. Thanks, sir. This is only my doubt. If it will be solved, please tell me.
Okay, okay. Okay, now let's go to the next slide.
Sir, Tuesday session is on Tuesday or
Tuesday, Tuesday.
some? Okay, okay. Monday session is today only, I guess.
Wait, wait, no.
Sir,
Actually,
Monday session is today, na?
no, I'm doing next Monday session today.
Next Monday means this week after जो week आएगा उसका.
Uh, because I have a exam. Like I have end semester exam.
Okay, okay.
Like this is 24th class, 24th April. So on 17th April there will be another session. So now we'll go over std colon colon function. So std colon colon function is a um, it is a template class. Okay, so it is a data type which is defined in the functional header. So this is, you can use it as an alternative to function pointers. Like they conceptually do the same thing, they are different. Like if something is using a accepting a function pointer, you cannot pass a std function, but the conceptually they do the same thing. Like for example in the table you can see that uh, so they have, in the first type they've declared a function pointer, which returns a int, and like it takes two integers and returns a int. So it can be replaced with this std function, and the syntax is also simpler. Here also, if you use a functor or a member function pointer, then that can also be replaced with std function. So here there is an example of std function. So you can see that some functions have been defined above. Okay, first one is a global function. Then we have a functor object because it overrides the call operator, and then we also have a struct with a member function. And then in the main class we are defining several std functions, which are pointing to those function. functions. Okay, we are defining some std function which is pointing to those functions, and then after defining them you can see how it's defined. We write std function, and then in the template argument we specify the type. What is the type of the function? And then we write name of the function object, and then equal to the function which we are using. And then after doing it we can call the functions as shown. So here we are using fn1, and in parenthesis we are writing 60, then we are writing fn2, in parenthesis we are writing 60. So like that we can call the functions also. This is an example with std functions. You can go over on your own. Next we will cover this generic or generalized lambdas. So this is very simple. This is like template arguments. This is like template arguments. Uh, so suppose we are writing a lambda function to add numbers. So we have to write a lambda function. Let us say we are adding integers. So we write a lambda function which takes two arguments, and it returns the sum of the integers. But then let us say that we want to add two double values. So then we'll have to write another lambda function for double, but the logic is the same. So in this case we will use we know that templates are suited for these purposes. When the logic is the same but the data type is different, we use templates. So we can write a templatized lambda function here, template, and then we specify the type name, and then instead of specifying the type we write TATB. Return type is also T, and return A plus B. But in C++14 there is another way to do this. Uh, Wait a minute. Okay, so in C++14 there is another way to do this. What we can do is that we can write auto in front of the keywords, and then the rest of it is same. So then the compiler will try to infer the type on its own, based on where it's used. If it is used in a if this lambda function is used with integers, then automatically it will be converted to a integer lambda function. So this is how we can write one lambda function for multiple data types. So there is an example here which says that how a lambda function without a capture list, with an empty capture list, it can be converted to a function pointer. So you can see over here, this is a function pointer, uh, int star fp, and in parentheses int. So the function takes one integer and it returns another integer. So we can assign a lambda function to this function pointer. This is an example of recursive lambda functions. This is an example of how we would write. So this is a function to count the number of ones in a binary number n. So normally we would write like this, okay, as a normal recursive function. Now see the problem with this is that normally we can use recursive functions quite easily. Okay, there is no problem. But using it with lambda functions is difficult because as you know, the lambda functions are small anonymized functions, so they might not have a name also. Okay, the lambda function might exist without a name. So then how do we call it inside the function body? Like there seems to be no way to call it so then there is no way to recurse. So the method is that we the method is that we assign the lambda function to a variable, and then in our capture block we write the same function, so then that function becomes available in the body. As you can see over here, first we write std function, which is the data type, and then we write a variable name. So this is we are declaring that we will write a function, and then we set this variable equal to the lambda function. Okay, so up till here it's, I think it's understandable. And then what we do is that in our capture list, in our lambda function capture list, we include the same variable as a reference. So then what happens is that this becomes available in the function body. Like we can use this function name in the body. So that way, see here it's written also capture count once as its free, as its use is free in the body, and then capture needed for count once now as it's a local symbol. Okay, so then this is how we can use recursive lambda functions. This is an example of co-recursive lambda function. So yes, so co-recursive, normally co-recursive function means there are two functions which call each other. So we have two functions f and g, and f calls g and g also calls f. So that way what happens is that there is a recursion, because f calls g and then g will again call back f, so it will recurse. But there will be a base case obviously, otherwise it will recurse forever. So this is an example with co-recursive lambda functions. I think you can go on your own, because if you understand this one, the recursive lambda functions, so this is similar. Okay, and then there are various examples of recursive lambda functions. Next we'll go over this, which is some advanced features of class C++11 features of classes. So the first one is the default and delete functions. So as you know that when we some many functions in a class are automatically written for us by the compiler. For example, that all uh, all classes normally get a default constructor, or you can get a default copy constructor. You will also get a default destructor. Unless you override any of these things, you will get them. So this equal to default. So what happens is that sometimes when we override the one function, another function's default value is also deleted. So what we can do is we can write equal to default to restore the default function. So that is default, and for equal to delete, what we can do is that equal to delete is used to specifically say that this function is not available. Okay, so you might now ask that if the function is not available, then don't write the function. But what happens is that some of the as I said, some of the functions are automatically created. So to explicitly prevent their creation, we can write equal to delete. For example, the first one is written here, that we can create a class that prevents it from being copied. So objects of the class won't be allowed to copy themselves. So how we can do is we can delete the copy constructor. But the problem is that the copy constructor is automatically created by the compiler. So then how do we remove it? So this is how we do it. We write the copy constructor and then we write equal to delete. So this explicitly tells the compiler that don't generate a copy constructor. Next we have this also. This is the second line also is a constructor. Okay. So we are deleting that also. So we have deleted two functions which are automatically created, and it prevents the copying the object. The other thing is that we can also explicitly say that we want the default copy behavior. So maybe because of something else we wrote, the default copy constructor is removed. So then what we can do is we can write the copy constructor and we can say equal to default. It means that it instructs the compiler that use the default behavior of the copy function. So see here it's explained. Special member functions are implicitly generated if used. For example, default constructors, destructors, copy operations, move operations. So these are some examples. These are some examples with delete. So here it states that deleted functions are defined, but they cannot be used. As you can see, like we have to write the function name. So we are in a way we are defining the function, but they cannot be used because we are saying that they have been deleted. So if the compiler finds that we have used the function somewhere, it will tell us that it is wrong. We cannot use. So these are some rules for moving. Okay, move rules. So if any move, copy or destructor is explicitly defined, then no move is generated by default. So all these rules are there. Okay, we'll go over this one, delegating constructors. So this is quite easy. Okay, simple to understand. So it just means that we can call another constructor from one constructor. So it prevents code repetition. Like let us say that we write a constructor which sets some value to set some variable to a value. Okay, and then like we have a constructor x and in parenthesis I, and then in the constructor we say x equal to I. So we are setting x to the constructor argument. Now to write a default constructor we'll have to repeat the same logic, but we just write x equal to 0. So it is repetition, code repetition. So instead of that, what we can do is from the default constructor we can call the specialized constructor with some arguments. Wait, this is a bit confusing argument. Okay. Uh, anyway, let us see. So So here you can see it's highlighted in red that we have a default constructor with no arguments, and it's doing this. Then we have a default constructor with double, and it is doing this. And all these three constructors, they are practically the same, just some uh, one two things are different. So what we can do is we can write one constructor, one generalized constructor that accepts. So here you can see in the next one it's defined. We are writing a generalized constructor that takes the size and the flex FL value also, and then it initializes the whole thing like this. And then for each of the specific constructors, like let us say the default constructor and the widget with the double FL and widget with the int sz, we can call this specific specialized constructor with the default values. So that is how we can reduce this code duplication. So then next we have in class member initializer. So this is also simple. So in C++03, when we are writing the class, only static const integer members can be initialized. Okay, so the initialization can be done at compile time. But in C++11, non-static data members may also be initialized. Next, this one talks about inheriting constructors. So I think so it is just like normal inheritance. You can go over it. Next, we have override and final. Override and final are explicitly used to specify like control overriding. For example, let us say we have a derived class where we are overriding some base class function. Okay, now there might be some silly mistake because of it. So there might be some silly mistake during the while overriding the function. So what we can do is we can specify that in the derived class we are specifying that we want to override the f function. So here, if you look here, your base class has a virtual function f, and in your derived class you are overriding it. Okay, but let us say that we forgot to write the f function in the base class. Then in the derived class there would not be any warning. Okay, there would not be any warning, and the problem would be difficult to detect, and it might slip through. So what we can do is we can explicitly say over here that we are overriding a f function. We are not defining a new f function from scratch. We are overriding it. So then the compiler will check whether already another f function exists or not. If it exists, then it's all right because another f function exists and you are overriding it. But if another function does not exist and you are just writing a new function, then it will throw an error. Similarly, we can mark a function as final. That will prevent it from getting overridden. We can also specify the final with a class, like class x final. This will prevent the class from getting inherited from. Next we have the explicit keyword. So the explicit keyword is used to explicitly define typecasting behaviors. So let us say we have a class and we are typecasting it using uh, static cast. So for most of the types we want the conversion to happen automatically, but for a few specified data types we can specify the conversion process by making a by writing like this. So we can write explicit and then operator class type, and then we can write this. Okay, so this will explicitly specify a conversion behavior for the static cast. So this is the last module we'll go over, then we'll start the exercises. Okay, so C++11 has introduced some non-class types. So for example, they are enum class and fixed with integer types, and generalized unions, and generalized PODs. So the first one is the enum class. So the old enum classes, they had a few problems, which is that they were implicitly converted to integers, and they exported the enumerations to the surrounding scope, which means that when after writing enum and then the inside the curly braces we write the enumeration values, they would be available in the global scope, which is not desired actually because it can cause name clashes. So here in the example you can see that we have written enum alert, and then the enumeration values are given. So these values will become available in the global scope with the old type of enum. So in the global scope, these keywords will start having some values like green, yellow, or red. So it will cause name clashes. So these problems are rectified with the new enum classes. So for that, what we simply do is we write enum, and then after that we write class, and then we define the enumeration as we previously did. Here you can see the advantages of using this method. You can see that it is not automatically converted to integer, or the reverse is also not done. Okay, it is not automatically converted to the color type object also. Next you can see that the in the with the old system, all these names like bronze, silver, gold, and then silver, gold, and silver, gold, platinum, all of them will be exposed into the global namespace, so there will be name clashes. With the new type of enum, with before using these names like bronze, silver, gold, we'll have to write the class name. Okay, like color colon colon bronze. Okay, so that is how it prevents the name clashes, because the enum type is also uh, prefixed before the actual enum, like color colon colon bronze, color colon colon silver. The other feature is that we can specify the underlying type. So we can just specify what type of integer we want it to be. Next, we have a few fixed with integer types. So this is quite useful if you are doing embedded systems programming, because the embedded systems programming usually have has these restrictions like you can only use 16-bit integers. Okay, or you might have to transfer data somewhere. For that you need the data in 8-bit format. So these data types are mostly useful for uh, embedded systems. So one of the data type is like int 8 underscore t. So this is an integer which is 8 bits long, and it is guaranteed. Okay, because you see the rest of the sizes, they are not guaranteed. Like if you write int, just plain int, then there is no guarantee that what size it will be on different machines. Like for example, on a Intel chip, the size of the plain int might be 16 bits, but on a ARM chip, the size of int might be different. Okay, it might be 32 bits. So to reduce this variability, what we can do is we can explicitly specify the size of the int. Like we can say int 8 underscore t, then the compiler will use the 8-bit version of integer only. It will not choose 16 or 32 or something. And then we have some other types like int fast and then the size. So it will choose the fastest signed integer type with at least n bits. Next also we have int least nt. So this will choose the smallest signed integer type with width of at least n bits. So the fast one will choose the fastest, and the least one will choose the smallest type with width of n bits. And int max t will choose the maximum with signed integer. So this is the difference between the types. So as I explained, the same thing is shown here with example. Next we have generalized unions. Uh, I will skip over this because we don't have time. This one also. Okay, let us go to the templates one. Okay, so in C++11 regarding templates, we have external templates, template aliases, variadic templates, local types as template arguments, right angle brackets, and variable templates. So the first one is super simple. We can, before a template, we can write extern. So it will allow us to define the template somewhere else. So in some other file, we might write template class my vector int, and in our main file we have to write extern template class. So this is basically a way of avoiding redundant work by the compiler. So we are not repeating the template definition. Next we have template aliases. This is also quite simple. So suppose we have a template with 3-4 types. Okay, 3-4 template arguments. We can create a new template out of it where we specify just 2 of the arguments. So now the new template is a more specialized version of the previous template, where 2 of the types have been fixed and the other 2 are still free. uh, Let me show example here. Okay, so this is a good example. So here we have a matrix class. We have a matrix class which is a templatized class that takes the data type t, the number of rows, and the number of columns. So the matrix class, as you know, a matrix is a rectangular array of numbers. So this matrix class takes the data type of the numbers and the number of rows and the number of columns. Okay, now out of this we can now create specialized versions of this template class like this. For example, we will specify using square equal to matrix t line. So it means that in the new version of this matrix class, the number of rows and the number of columns are equal. So it's a square matrix. Next, we can also specify that using vector equal to matrix line comma 1. So in this, it means that in this specialized version, the number of columns is 1. Next we have variadic templates. So, so this might be a bit difficult to understand. Okay, variadic templates means that we'll accept a variable number of template arguments. So this is sometimes necessary to do. Okay, generally it is not required, but for a few special cases it is required. So this is how we do it. We write in the usual way. We write template and then type name t, and then we have to write type name dot 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 and then the args list. Okay, so that is how we do it. So we use dot dot dots to, like, three dots to specify a variable number of arguments, and we process it like this. We one by one we take out all the arguments. So here it's written that peel off the first argument. So how do we do that? We write the first argument explicitly as t value, and the rest of it we use dot dot dots, three dots. The rest of the arguments we write it over here as args dot dot dot. This So it creates a recursive. When this template is expanded by the compiler, it creates a recursive function call. So let us say in our code we use printf with 5 arguments. So then one printf function will be created which has 5 arguments. In that printf function, one argument will be processed, and then again the printf function will be called, but this time with 4 arguments, and then with 3 arguments, and then 2 arguments. Like this it will decrease until the printf function will be called with no arguments, and that will be the uh, base case. It will be the base scenario. So here you can see a simple example uh, for a adder function with variadic templates. So we write t adder and then t first and the rest of the arguments. Okay, now in the shown example, they now call adder with 5 arguments. Okay, here you can then see that adder is called with 5 arguments, where first argument is taken out. Okay, t equal to int means that the first argument has been taken out, and then the rest 4 are there in the args list. Then that function calls another function where again the first argument is taken out. So now the args list contains 3 arguments. Then the args list contains 2 arguments. Like this it decreases. So from 4 to 3 to 2 to 1. So till like this it decreases until the last adder function is called with just 1 argument. And this is the base case. So here the recursion will stop. And here are some other examples. Next we have this. So till C++, 03, if we had a nested template, then like while closing a nested template class we use this double angular brackets, but this used to be like this got confused with the right shift operator. Okay, so the way was that we needed an extra space between the angular brackets, but from C++, 11 the we can use this closing brace without the extra space. We can use the angular bracket without the extra space. Okay, so this is all. Um, so the summary part of today's session is complete. Now we'll solve the exercises. Um, we'll start in 2 minutes. Okay, I will come in 2 minutes. Okay, thank you for waiting. Let us now begin. So this is the first question. Please try on your own for a couple of minutes. So in this question, wait. So this question is about universal references. So universal references are these kinds of, okay, where the data type is not specified. So when we write auto ampersand, or when we write template ampersand, these are universal references because they can bind to anything. Like they can bind to any data type. The data type is not specified. So because of this, the universal references here are this auto ampersand and t ampersand. Okay. The other ones, their types are specified. For example, this one is a integer and this one is a vector. Okay, although the kind of vector is not specified, but it's the vector, so it's not universal. So here the answer will be B and C. Okay, they are universal references. So any questions up till now?
Sir, what is the data type of n here?
Data type of n. That is not specified, na. It's a function that we are writing. So it is like
So, sir, there will be no clash between because T will be T ampersand and ampersand.
t will be
I value T will be integer ampersand, right?
in which line?
Line number 3.
No, integer is not specified, na. Nowhere here integer is written,
Okay, sir. Okay, sir.
and that is why it's
I
a
thought it was
uh,
tricky question.
that is why it is uh, universal, because any data type can bind in this
So
situation.
we considered data type of n as int only.
No, for n it's not specified. N1 it's specified. Okay, n1 is specified here as integer reference. For n it's not specified.
Okay, sir. So it depend on us what we pass.
We can, like, if we pass a double value like this, then n will be double.
Okay, sir. Thank you.
This is the second question. Please try.
Sir, option B.
Yes, it's correct. Yes, so in this case, the answer is option B. Okay, so here you can see we have two functions. One accepts the reference. So the first two overloaded functions. So first one accepts the reference and prints L value. The second one accepts this universal, not universal, it accepts this reference of reference and prints prints R value. Then we have a template function called wrapper which accepts two arguments n1 n2, and then it calls the functions based on various things. Okay, uh, and then in the main code we have an integer I, and we are calling wrapper with I and std move I. So when the function is called, then n1 takes the value of I and n2 takes the value of std move I. So what happens is that then when we call, so in the first case, uh, so in the first case, this is called the, so see n1 becomes the L value, so because of this the first argument is called. In the second line n2 becomes a L value again, so the first one is called. Then we are calling it with std move. Now as you know, std move produces a R value, so the third and the fourth lines, they have R value. Now coming to the last line, we have fun, and then we are calling std forward t and std forward u. Okay, so now here you must notice one thing. So std forward, what it does is that it forwards the argument with the same, like if it's a L value, it will remain a L value. If it's a R value, it will remain a R value. So that is why when we are originally calling the wrapper function, we have I and std move I. So we have I and std move I. So this now calls fun with the same kinds of, with the same value basically. So that is why one of them is a L value and the other one is a R value. So the first one is a normal I, okay, it's a normal variable, so that is why it's a L value. And in the second case, it is a std move I, so it produces a R value. So that is why like it produces a sequence of outputs like this. Okay, okay, then let us proceed. So this is the third question. Please try. Okay, so in this question, wait a minute. So in this question, the answer is B and C. Okay, so this question is about the new kind of enum classes. So here in the top you can see there are three types of enums. So I mean three enums and two types of enums. So the tint is the old kind of enum, and then the first two enums, color and signal, they are of the new kind, enum class signal and enum class color. So these three enums have been declared, and then within the function body we are now checking for various things. Okay, so now coming to the first function, this is absolutely perfect because we are taking a color kind of enum, and then we are checking whether it's red or not, and then we are returning true or false. So this is fine. Okay, it won't generate a compiler error. In the second function we are testing whether the color is green or not, but note here that it's a color, okay, color call, and then we are comparing it with a signal green. Okay, now obviously, like logically this does not make sense. Okay, if it was the previous kind of enum, let us say it was not the new kind of enum, it was the previous kind of enum, then this would work. Why? Because the enums are implicitly converted to integers, so they would be converted to integers and they will be compared, and it would match also. Okay, but in this case it gives a compiler error because the compiler will say that they're different types of enums, you cannot compare within them, so you cannot say that a color is equal to a signal. So this will generate a error. And next we have this yellow one. So here also you see we are comparing call equal to yellow, but this yellow it's not available in the global namespace. Okay, if we had used the previous kind of enum, then it would be available. Okay, wait, sorry. So this yellow is actually available in the global namespace also. Why? Because of this enum tint. Okay, the enum tint class, it's a old kind of enum, and it has the enumerations red, green and yellow. So these literals, okay, red, green and yellow, they will be available in the global namespace. Okay, so that is fine, but what will happen is that the enums are, the old kind of enums are implicitly converted to integers, right? So this yellow will be replaced with an integer here. Okay, but even then it will generate an error because you cannot compare the new kind of, so the new enum class, it is not compared, it cannot be compared with integers because like they want to separate this concept that the enum has to be an integer. Okay, because that might generate some problems because implicitly things will get converted and it will cause problems. So wherever there is a, so basically the main thing is this, that the enum class is not converted to an integer here. So hence this comparison will not take place. Okay, comparison will not take place, and it will give error. Now since it's not compiling only, so this success message will not be printed. So hence the answers are B and C. Okay, any questions on this one? Next we have this as question 4. This is on variadic templates. Please try on your own first. Okay, now let us do this. So the question states that identify the appropriate return line statement at line 1 over here such that the function findMax finds out the maximum element from the given argument list. So, uh, so how would we approach it? So this is so in variadic templates we have a variable number of arguments, as you know. So that template expansion, it is done in a recursive manner. Okay, until it comes to a base class. I mean a base case. So in any recursion we need a base case. So this first function, this is the base case. Okay. So when we find the maximum, okay, what we can do is we can recursively find out the maximum of smaller and smaller subarrays. Okay, until we come to just a list with one element. So maximum of a one element list is the value itself, right? So here that is written. So here if we are told that find max and t just one argument is there, so then the maximum will be that only. Okay, so this is the base case. Now we come to the recursive case. So here we are calling find max. uh, we are peeling off the first argument and we are writing the rest of the argument as this list. Okay, rx dot 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 and r's. Okay, so then what do we have to return over here? So if you know like if you have a list, okay, let us say if you have a list 1 2 3 4 5, one thing you can, if you had to find out the maximum recursively, what you can do is that you can find out the maximum of the rest of the list and you can compare it with the first element, right? You can say, so you can write something like this. So this is a recursive way to do it. This is a recursive way to do it. The same thing will apply over here. So this is the base case already, and over here the, so first we will so that t, this small t, this is the first argument, so this corresponds to this. Okay, so the answer should be something like this, that if t is greater than the, see the answer is d. Okay, so let me explain. So if t is greater than the find max of the rest of the list, so over here you can see that the small args variable, it stores the rest of the arguments. So if t is greater than the rest of the list, so it means that the first argument is greater than the rest of the maximum of the rest of the list. So then return the first item, or else you return the maximum of the rest of the list. Okay, so if t is greater than the rest of the list, then you return t, else you return find max of args. So this is, so d is the answer. If you replace it here, it will find out the maximum. So any questions till now? Okay, then let us continue. This is the next question. Please try.
Sir, option D.
And no, no, the D is not the right answer. So note it here. Okay, this is in C++11. D would be the right answer in C++03. Okay, so in this question, the answer will be B. Okay, so so first we have a templatized function called process, which has a accepts a template type name T, a vector of a vector of type P, and then in the function we are making a functor object. Okay, this compare is a functor object. Why? Because it overloads the call operator like this. Okay, and it returns a greater than b. So so this is a functor object. Then we are calling the sort function with the vectors begin and end pointers, and with this functor object. Now the sort, now this third argument of the sort, it accepts a function which will say whether one element is less than the other. Okay, so if we have to supply a function that will say whether one element is less than the other. Okay, so if we pass this, then the sort function, it sorts in ascending order. Okay, but if we have to reverse this, then we just pass a function which it returns this. Okay, it returns the greater than sign, then it sorts in reverse order, descending order. Okay, so now and in the main function we have a vector, and we are calling process with the vector, and then we are just printing the vector. So the main function is simple. Now what somebody said that it will throw a, it will there will be a compiler error at line 1, because this compare this compare struct, okay, this is a local object, okay, of the inside the process function. So it's a local object, so how will it work? It will not be in the scope. So that was the problem in C++03, but in from C++11 you can pass local objects also. Okay, so this will work well, like this will work normally, and it will sort this list in descending order. So this will be the output. B will be the output. So any questions till now? Okay, then let us continue. This is the next question. Please try.
Sir, option C.
Okay, see, there is another option. There are two options.
Option A.
Yes, option A and C. Okay, so in this question, we have two variables, sum and multi, and then here we are basically writing a lambda function, and then we are calling the function here, uh, and the result is stored in result. Okay, and then we are printing it. So you see that the sum of the, if you see the function body, then the product is stored in multi. Okay, but the sum is returned. The sum is the output of the function, so the sum will be stored in the result variable. We will have to somehow get this multi. Okay, multi variable. So the multi variable has to be accessed from within the lambda function. Okay, so how do we do it? As you know that when we have to access the context, we have to pass it in the capture list. Okay, so now here there are four lambda functions. Here there are four lambda functions. So the first one, it is of type auto process equal to ampersand multi int xy. Okay, so wait a minute. Okay, yes, auto process equal to ampersand multi int xy. So in this case, the lambda function, it accepts two arguments x and y, and in the capture list it has ampersand multi. So this is a reference to the multi variable. Okay, multi variable, this one. And now since it's a reference, you can modify it inside the lambda function as such, like this. Okay, and you can return the sum also. Now coming to the second one, so this will work. Okay, now coming to the second one, it is similar to the previous one, but in the capture block we have sum and multi. Okay, now the problem is that these are passed by value. Okay, since the ampersand is missing, these are passed by value, so the changes you do here, it won't be reflected outside. So the multiplication result will not come. Then we come to the C, third one. In the capture block we write ampersand. So this means that it captures all the variables as a reference. Okay, so all the variables. So obviously both sum and multi will be captured like this. So this will also work. And in the last one, in the square brackets we write equal to. So this will pass all the variables as a value. So as you saw from the B option, if you pass by value, then the changes are not reflected. So the D option will also not work. So the answers are A and C. Okay, then let us proceed now. This is the seventh question. Please try on your own. Okay, in this question, so we are giving the lambda function over here, and we are told to identify the equivalent closure object of the above lambda function. So you can think of it as that we will identify the equivalent piece of code which will give the same result. Okay, so you can think of it like that. So first let us understand what the lambda function is doing. See, yes, Anuma is correct, it will be C. So first let us understand what the lambda function is doing. So first, in the lambda function we have a capture block where we are capturing interval by value and result by reference. So interval by value and result by reference. And then in the argument it accepts one argument val, and then it stores val plus interval in result, and it prints this thing. It prints val. It prints this message with the values of the variables. So now we have to find the equivalent code here which does the same thing. So first you can see that so in all of these classes, okay, in all of these structs, we have some data members. We have a constructor. This is a constructor, and then we have the call operator. We are overriding the call operator. So this turns this class into a functor object. Okay, so So see, first in this function, lambda function, we know that it accepts only one argument, okay, int val. So we can exclude any functor objects which take more than one argument, which for example d, okay. So in d, the call operator, it takes more than one argument, it takes val and result. So that is obviously not the same, so the function signature is not matching, so d won't be the case. Okay, then you can see that this takes the result as a reference and the interval as by value. So you have to see here which one takes the uh, interval by value and result by reference. So in A and B, it takes the interval as a reference here, okay, and the result by value. So this will not work and this will also not work. But for C, you can see that it takes the interval as value and the result as reference. So all of the things match over here. Uh, you have the data members, and then you have the constructor which initializes this, and then you have the call operator which accepts one argument as shown here, call operator, and it returns the result. I mean, it stores the result in the uh, data member and it prints the message. So the answer is C. Okay, now any questions on this one? Okay, fine, then let us continue. So this is the next question. Please try. Okay, so here the answer is B. Okay, uh, so in this question, first uh, base class has been declared, which is called data. So a data base class has been declared, which has a constructor, and it also has a data member d1. So this constructor, it prints constructor 1. Then we have a derived class from this base class. Okay, so we have a derived class. And we have a default constructor here. Then we have a constructor which takes one argument, and it calls another constructor of the same class with the argument and another value 0.0f. So this is an example of delegated constructors, as we saw in the PPT. So this is an example of delegated constructor. So this will now see here the second argument, it is suffixed with f. So it means that this is a float. So out of these constructors, this is the float one. So this will call this. Okay, the first constructor will call the float constructor over here. Now see the float constructor in turn again delegates it. Okay, it calls another constructor with d1 d2 and the string unknown. Now where is this constructor? This constructor is in the private section. Okay, private section we have d1 d2 and string. Okay, so this constructor will in turn call this function, and over here this does not delegate any further. It sets the value of these variables and it prints setter 5. Now one thing to note here, that over here while initializing the values, it initializes the base class also. Okay, and as you can see that the base class prints constructor 1. Okay, so if we look at the call, like the call stack, if we look at the call stack, then this one, okay, I'm writing data 100. Okay, so data 100 calls constructor 2. Okay, this one, it calls this one, so it calls constructor 2. And then constructor 2 calls constructor 4. Constructor 4 again calls constructor 5. But before constructor 5's body is executed, constructor 1 is called. Okay, and then after 1 returns, then 5 is called again. So if we see the output, okay, now see all these print statements, they are in the body of the constructor. So they are done when the initializer list is processed. Okay, so if we look at the how things will be printed, so first this call will call this 2, then it will call 4, then that will again call 1. So the first one, so this constructor, it will initialize the value at the first. Okay, that is the only constructor that will finish first. So it will then run the function body and it will print setter 1. Okay, and it will now return, it will return back to 5. Actually, wait, there is a mistake here. This will call 5 and then 5 will call 1 and then it will return. So the order will be the returning order, the order it follows while returning. So first constructor 1 will be printed, then it returns here, then 5 finishes doing the 5 goes over the initializer list and then it will run its own function body which will print setter 5, then it will return back to 4. 4 will finish doing the initialization and it will run its own body, and it will print seater, it will print seater 4, and then again it will go to 2, and then finally 2 will finish doing its uh, initializer list, and it will run the function body, and it will write this. So this will be the output, and this is option B. Okay, any questions till now?
No, sir.
Okay, then I would like to conclude today's session. Okay, so thank you for attending. That is all I have today. Okay, and the next session will be on this Monday only, so day after tomorrow.
Thank you, sir.